Okay, so we should be able to figure this out for any orbital that we're discussing. And when we can figure out especially radial nodes, we have a good head start on going ahead and thinking about drawing radial probability distributions. We did it for the s orbitals. We can also do it for the p. We can do it for the d. All we have to figure out is how many nodes we're dealing with, and then we can get the general shape of the graph here. So let's actually compare the radial probability distribution of p orbitals to what we've already looked at, which are s orbitals, and we'll find that we can get some information out of comparing these graphs. So if we draw the 2p orbital, what we just figured out was there should be 0 radial nodes, so that's what we see here. The other thing that I want you to notice is if you look at the most probable radius, for the 2s orbital, it's actually out further away from the nucleus than it is for the 2p orbital. So what we can say here is that the 2p is less than or smaller than the 2s orbital. So think about what that means. We're, of course, not talking about this in classical terms. So what it means is if we have an electron in the 2p orbital, it's more likely, the probability is that it will be closer to the nucleus than it would be if it were in the 2s orbital. We can also take a look at the 3s, which we have looked at before, and we figured out that that should have 2 radial nodes. We can look at the 2p, which should have 1 radial node, and we just figured it out for the 3p has 1 radial node, and for the 3d here, we should have 0 radial nodes. We just calculated that. So again, what we see is the same pattern, where the most probable radius, if we talk about it in terms of the d, that's going to be smaller than for the p, and the 3p most probable radius is going to be closer to the nucleus than it is for the 3s most probable radius that we're looking at. So there are 2 different things that we can compare when we're comparing graphs of radial probability distribution. And the first thing we can do is think about, well, how does the radius change, or the most probable radius change, when we're increasing n, when we're increasing the principal quantum number here? So from going from the shell of n equals 2, let's say, to the shell of n equals 3. And what we find is we're going from about, or exactly 6a0 here, to almost 3 times that when we're going from 2s to 3s. So we say as n increases, the orbital size is also going to increase. And when we talk about size, I'm again just going to say the stipulation that we're talking about probability. We're not talking about an absolute classical concept here. But in general, we're going to picture it being much further away from the nucleus as we move up in terms of n. The other thing that we took note as is what happens as L increases, and specifically as L increases for any given principal quantum number. So if we're keeping n the same, we look, and what we saw was that the size actually decreases as we increase the value of L. So I want to contrast that with another concept that seem to be opposing ideas, and that is thinking about not how far away the most probable radius is, but thinking about how close an electron can get to the nucleus if it's actually in that orbital. And what we'll find is that we actually see the opposite. So if we compare L increasing here, so a 3s to a 3p to a 3d, what we find is that it's only in the s orbital that we have a significant probability of actually getting very close to the nucleus. So if I kind of circle where the probability gets somewhat substantial here, you can see we're much closer to the nucleus at the s orbital than we are for the p than when we are for the d. So that the size still for an s orbital is larger than for a d orbital, but what we say is that an s electron can actually penetrate closer to the nucleus. There's some probability that it can get very, very close to the nucleus, and that probability is actually substantial. A kind of consequence of this is if we're thinking about a multi-electron atom, which we'll get to in a minute, where electrons can shield each other from the pull of the nucleus, we're going to say that the electrons in the s orbitals are actually the least shielded. And the reason that they're the least shielded is because they can get closest to the nucleus. So we can think of them as not getting blocked by a bunch of other electrons, because there's some probability that they can actually work their way all the way into the nucleus. So this is a concept that's going to become really important soon when we're talking about multi-electron atoms, and I just want to introduce it here. here that it is sort of opposing ideas that even though the s is the biggest and it's most likely that the electron is going to be furthest away from the nucleus, that's also the orbital in which the electron can, in fact, penetrate closest.